Okay, hi everybody. So today we're going to continue talking about social choice. So to just give you a bit of background about my reasoning for the choice of topics to cover in social choice. Initially, the idea was to do 3 social choice lectures. That's still the plan. But initially, I thought I would do one sort of background lecture, which is what we did, and then 2 lectures on statistical approaches, which is stuff that is closer to the kind of Bayesian reasoning we did in other parts of the course and closer to machine learning and also closer to applications. But then when I sat down to actually make the slides, I figured it would actually be really good to do this manipulation lecture that we're going to do today. And I guess there are several reasons. One is that it's just a really interesting topic that I want you to know about. The second is that it's something that a lot of people in AI are thinking about as part of the longer term planning aspects of multi-agent systems. So it's something that's not as close to applications, but definitely a very interesting long-term consideration. And the third is that it's sort of a topic at the intersection of social choice and game theory, and specifically is related to an area of game theory called mechanism design. So that's an area that we're not going to cover on its own, but I think it's really good for you to see, get a taste of that area through this intersection with social choice. So those are on a high level, why I changed the schedule a bit. For those of you who noticed the schedule until a week ago. So we're going to do this manipulation lecture and then talk about statistical approaches in the next lecture. Okay, so let me just remind you some of the terminology and notation from last time. So we talked about a set of voters that we denote by integers 1 to n, and the set itself is capital N. We have a set of alternatives, m alternatives, that we denote by capital A. And we said each voter has a ranking over the alternatives. Now I'm going to introduce one new small notation, which is when I write x is the squiggly greater than sub I of y, that means x is preferred to y by voter I. So according to the ranking of I, x is ranked above y. So that's a notation we'll use quite a bit. And we also talked about preference profiles, which are vectors of rankings, ranking per each voter. So we're going to denote a preference profile as a vector of this squiggly greater than notation. Okay, so this means every voter has a preference of this type, greater than sub I, which gives all of the pairwise comparisons between different alternatives for that voter. And like before, a voting rule F is a function from preference profiles to alternatives that tells us, given the preferences of the voters, it singles out the winning alternatives. Now, one difference from last lecture is that last lecture we didn't talk about incentives at all, so we implicitly assume that voters are honest. So they're, whatever they're saying actually reflects their preferences. And what we'll do today is think about the more realistic case, especially when we think about subjective preferences where the voters can act strategically. And then the question is, how bad is this problem and how can we circumvent it? So here's an example just to illustrate this problem of manipulation in elections. On a high level, the issue is that voters may report preferences that are not the real preferences and end up getting an outcome that is better according to their real preferences. So let's see an example. We're going to use Borda count. So with 4 alternatives, that means each voter gives 3 points to the first place, 2 points to the second, 1 point to the third, and 0 points to the last. And remember that we just choose the alternative that has the most points overall across voters. So we have 3 voters here. Now look at this profile over here. So let's count how many points each alternative has. B has 3 plus 3 plus 2, that's 8 points. A has 2 plus 2 plus 3, that's 7 points. And obviously C and D have fewer points. C has 3, D has 0. So alternative B is the winner in this profile, right, in this one, with 8 points. Now, let's take the point of view of voter 3. And he's thinking, well, I'm getting B, which is my second choice, but maybe I can do better. And it turns out he can. So what he can do, here what I've done is I've kept the rankings of voters 1 and 2, but I've changed the ranking of voter 3. So now imagine that instead, like before, he ranks A first, but he lies and he says, oh, I actually really hate B. That's my most hated alternative. So now in this profile, A would still have 7 points. But now B has only 3 plus 3 plus 0 points. That's 6 points overall. Right, so what happened here is 3, by changing his vote, he was able to get A selected instead of B. And if you go back and look at his real ranking, A is preferred by this voter to B. Okay, so what he did was he reported an untruthful preference. He lied about his preferences, but he was able to get a better outcome according to his original preferences. He was able to get A instead of B that he prefers in the original profile. Okay, is this clear? So this is just one example of manipulation under Borda count. Now, to give you some historical background for this, who is this Borda guy? So he was actually a contemporary of Condorcet we talked about last time. He was an 18th century French nobleman. Like Condorcet, was a member of the French Academy of Sciences. And when he came up with Borda count, he actually suggested it as a voting rule for making decisions in the French Academy of Sciences. He presented this to his peers, and they examined it. And after looking at it, they came back to him and said, Monsieur Borda, there's an issue with your voting rule. It's highly manipulable in the sense that there are sort of many opportunities to lie about your preferences and get a better outcome like the one that we just saw. And Borda's immortal response was, my scheme is only intended for honest men. So he was pretty naive about these strategic aspects. Another fun anecdote about this is that I would like to tell you this guy is Borda, but there are actually no good pictures of Borda online. So in desperation, I ended up literally Googling for random 18th century French dude, and this guy showed up. I have no idea who this guy in the picture is. But anyway, what we want to do, we don't want to be naive like Borda, so we do want to think, especially in this lecture, about the strategic aspects of voting and how to avoid this problem of people lying about their preferences to get a better outcome. So let's, the main definition for this lecture is this idea of a strategy-proof voting rule. One way to say this is that we want truth-telling to be a dominant strategy. So we want it to be the case that no matter what other voters do, you're always better off telling the truth than lying about your preferences. So that's the idea. So here's how we write this using our notations. And notice this is going to be quite similar to the definition of Nash equilibrium, but I'll point out the important difference. So what is this saying? For every preference profile, and for every voter, and for every possible different ranking that voter I could switch to, the outcome of the voting rule according to the original profile is preferred according to I's real preferences to the outcome under the voting rule when I changes his ranking to this alternative ranking with the prime. Okay, so this is quite, when we talked about Nash equilibrium, we said it's a vector of strategies, it's the strategy profile, such that each voter has utility which is at least as high under the original profile as when the voter changes their preferences. So this is saying sort of the same thing. It's saying, now instead of a utility function, we have the true preferences, and we're saying the outcome of the rule under the original profile is preferred according to I's true preferences to the outcome when I changes his vote. Okay, so this is quite similar to the definition of Nash equilibrium. One big difference here is the addition of for every preference profile. Right? Because when we talked about Nash equilibrium, we said this is one particular strategy profile such that nobody wants to deviate given that everybody is playing in a specific way. And this is a much stronger definition. So this is saying for any vector strategies that sort of represent people's true preferences, they're always better off, under the true outcome than if they switch to something else. Okay, so this is sort of the difference between Nash equilibrium and a dominant strategy, right? So here we want truth-telling to be a dominant strategy in this game. So it's a very strong definition. Yeah?
Can you be a bit more precise about the definition? So what is the output of F? What's the result of F?
Right, so the result of F is an alternative, right? So F is a voting rule. It's a function from preference profiles to alternatives.
Okay.
So F of this preference profile is one alternative. Right, so it's like, if we go back to the example, so we're saying under Borda count, if you apply to this profile, the outcome is B.
Okay.
If you apply to this profile, the outcome is A.
So it's just one person.
And then, right, so just one person changes vote. And what this is saying is the outcome, which is B, under the original ranking should be better than the output, which is A, under under this manipulated ranking. Okay, so this doesn't hold here, but that's what we're asking for. So what the property we would want is the outcome of Borda count here, according to this ranking, should be higher ranked or the same as the output under this manipulated profile. Okay, but really the intuition is very simple. So it just says, in no situation should you get a better outcome if you lie about your preferences. Any other questions about this, Ankush?
So when you say greater than equal to I, that means that this alternative is preferred by I over the other preference, right?
Or they're the same. That's actually a good point. So I've introduced this greater than or equal thing, which means like either the voters have strict rankings of the alternatives, but this is saying, either the outcome didn't change, or if it changed, it had to change to something that I like less.
Right.
Okay, so it also could be the case that I changed my vote and the outcome didn't change. That's fine as well.
And that preference, so that preference is in the preference profile I prime or the preference profile I?
Which
So
one?
when you say greater than, this.
Yeah, so this is looking at the original, we're looking at some preference profile. We're looking at the original preferences of voter I.
Original, not
Yeah, exactly, yeah. Yeah, so what we want to say is like, according to your true preferences, the original ones, if you change to something else, you're going to get a less preferred outcome according to the original preferences.
Yes. Okay.
Yeah.
So this rule assumes that nobody else is manipulating, but if everyone is manipulating, then everyone knows that everyone is also doing that.
Right, so this is not assuming that, but this is a good point. So this is saying, whatever others are doing, whether they're telling the truth or not, right? This is not making an assumption that in this preference profile, everybody else is telling the truth. So this is this very strong dominant strategy, definition, which says, just fix the rankings submitted by the others to anything and call it this profile. And this is just saying, from the point of view of I, he's better according to the original ranking than any other ranking. But this is not actually making any assumption whether the others are manipulating or not. Okay, so this is an important point because it's a very strong definition, and what we'll see is that it's difficult to obtain. So you could say, okay, so what if we relax this very strong definition, and we'll talk about some of these aspects later. But this is what we would ideally want. So it's like a very worst case definition. Like whatever happens, whatever other voters are doing, we don't want any voter to be able to gain by lying about their preferences. Okay, so here's poll number 1 for you. So think about plurality, the most simple rule where every voter just gives 1 point to his favorite alternative. And the question is, what's the maximum value of M, the number of alternatives, such that plurality is strategy proof? 2, 3, 4, or infinity, which means it's always strategy proof, like no matter what. More seconds. Okay, interesting. So a plurality of you think that 2 is the right answer, but then there's also like quite a bit of support for the opposite answer, which is it's always strategy proof. So 2 is actually the right answer. That's the maximum value. So let's think about it. So first, this is sort of implied by the question statement, but can somebody give an argument for why, for the case of 2 alternatives, plurality is strategy proof? Kush?
Because if you, I mean, you only have two possible voting preferences. So if you switch your voting preference, then you're only hurting the candidate that you really wanted to win.
Excellent. Excellent. Okay, this is like a really concise argument. And Kush is saying, well, you just have two options, right? If, so think about it this way. If your candidate is already being selected, you're happy, like you can do better with the other candidate. If the candidate you like better, the one that you're putting first, is not selected, the only thing you can do is switch him to the second place, and then you're only giving a point to the other guy, which is only hurting your candidate, like definitely not making them win. And that's basically the only two situations you might have. So for two alternatives, plurality would be strategy proof. In fact, it coincides with just majority voting. So it would just coincide with looking at the two alternatives, who has like the preferences of the majority of voters. But what about, so I claim that for three alternatives already, plurality wouldn't be strategy proof. So could somebody give intuition for why this is actually something that happens in political elections quite a bit? Matthew?
Let's say you've got two choices that are tied, and essentially you're the tiebreaker vote, but you prefer the third choice.
Excellent.
If you prefer one of the two that are tied instead of, then it would be better to vote for that.
Excellent. Right, that's exactly right. And this is something people often talk about in political elections. Bush, Gore, and Nader is like one classic example, right, of like this spoiler candidate. So, but essentially the idea is if you have a third candidate who has no chance of winning, a lot of voters, instead of like wasting their vote on this third candidate, would prefer to break, what might be a tie. You actually affect the outcome only if there's a tie, which is very unlikely in like U.S. national elections. But still a lot of people would prefer to vote for one of the candidates that maybe, even if they want a third candidate the most, you would prefer to vote for one of the candidates who actually has a chance of winning. And the extreme case, like Matthew said, is sort of, that there's an exact tie between two of the candidates. It depends on tie breaking. So let's say the tie is broken against the candidate that you like. And then instead of voting for the third guy who's like way below, you just you change your vote to your second choice, let's say, and then break the tie in favor of that alternative. So this is a pretty intuitive situation that often happens, and like is a real issue with political elections. So okay, so what we just said is plurality also has the same issue. So in order to reason about this kind of stuff more generally, I want to introduce a few terms, and then we'll state a very, very powerful and fascinating theorem called the Gilbert-Satterthwaite theorem. So we need a few definitions, like I said. The first one is a dictatorship. So we say that the voting rule is dictatorial if there is a voter who always gets his most preferred alternative. So the idea is that there's some voter, let's say voter number 1, such that the only thing the voting rule does is look at the preferences of voter number 1 in the given profile and chooses voter number 1's most preferred alternative. Okay, so there could be that dictator could be voter number 1, number 2, number 3, up to number n. So you have like n possible dictatorships, one for each voter. But that's essentially all a dictatorial voting rule can do. So that's obviously like a very, very bad voting rule. So here's another very simple voting rule, a constant voting rule, which just always does the same thing. So no matter what the given preference profile is, it always chooses the same alternative. So let's say alternative A will get selected like no matter what the preference profile is. So it's just a constant function as a function from preference profiles to alternatives. So I've actually, like when I first created this slide, I was thinking, oh, Queen Elizabeth would be like a nice example of this. And I thought, oh, maybe I'll be able to find two like quite similar pictures of her. But then I ended up finding these two pictures like independently. These are like two, they didn't appear in the same place. But like nothing has changed over like, 60 years. It's pretty amazing. Anyway, by the way, if you haven't watched the Netflix show The Crown, it's really, really good. It's about Queen Elizabeth. Really highly recommended. Anyway, so what I want to claim is, for dictatorships and constant functions, these kind of voting rules are actually strategy proof, which is pretty easy to see. a constant function. Why is it strategy proof? Because whatever you say doesn't matter. The same alternative would always be selected. So you can do better by lying about your preferences. Why is a dictatorship strategy proof? Well, if you're the dictator, you always get what you want, so you can't benefit from lying. If you're not the dictator, nobody cares what you want, so you also can't benefit from lying. So any of these would actually be strategy proof. And what the Gilbert-Satterthwaite theorem says is that these are essentially the only voting rules that are strategy proof. So let's just define, another very simple definition. We say that the voting rule is onto if any alternative can win. So it just says, as a function, again, from preference profiles to alternatives, it's onto its range, onto the set of alternatives. Right, and what the theorem says, so this was proven independently by Gibbard in 73 and Satterthwaite in 75. So it says that if there are at least 3 alternatives, then any voting rule that is strategy proof and onto has to be a dictatorship. So the contrapositive is that any voting rule that is onto and non-dictatorial has to be manipulable, in the sense that there will be situations where some voter can get a better outcome by lying about their preferences. So one observation is, again, the m greater or equal than 3 condition is obviously necessary, because if you have m equals 2, we saw that even plurality would be strategy proof. So really you need the range to be of size at least 3. But still, this is a pretty devastating theorem, right? I think it was like a big shock in the 70s. Some people interpret it as saying that dictatorship is like a good system of government. I don't know if that's the right interpretation, but it is. I think it's pretty striking that you can say something about a problem that's so real in such abstract mathematical terms. So to me, it's like a really beautiful theorem. In fact, the first time I ever heard about social choice, I think I was a second-year undergrad, and I went to this just this random lecture that was about the Gilbert-Satterthwaite theorem, and I thought it was amazing. So this is to me like a really, really beautiful theorem that really says something very real about the real world, and politics as well. So so like I said, this was pretty devastating, and this is 73, 75. So since then, people have spent decades thinking about, how can we circumvent this devastating result, and still prevent the situation where people are manipulating in elections. And again, people have often thought about this in the context of political elections, but like we discussed and we'll discuss more, voting is also just a mechanism for making decisions. So this is also relevant to making decisions in small groups or in multi-agent systems where you need some mechanism for consensus decision-making among agents. These are things that are very relevant. In fact, some would argue this kind of stuff is even more relevant in a multi-agent system where the agents are software agents and they're sort of hyper-rational, whereas people are not always very rational and may not take an opportunity to manipulate if one exists. So this might even be more relevant in a multi-agent system. So here are a few of the things people have talked about over the years in order to circumvent the Gilbert-Satterthwaite theorem. So one idea is restricting the preferences. One condition that's implicit in the theorem is assuming that people can cast any ranking over the alternatives. And what we'll see on the next slides is that if you assume more structure on what the preferences look like, you can actually get some positive results. A second area is assuming that we have money. So money allows us to align the incentives of players or voters with our goal as the designers. And this leads to the core of what people usually talk about in mechanism design. So mechanism design, the most popular kind of question is how to design the rules of the game in a way that incentivizes all of the players to tell the truth. And part of the tools that you have is how to set up payments in an auction, for example, in order to elicit truth-telling. So this is something, the stuff we're talking about is very closely related to this area, but we're not going to talk directly about these cases where you have money, like auctions. But this is something that there's, obviously a lot of work in this area. And the third topic that we will cover later is talking about computational complexity in order to circumvent the Gilbert-Satterthwaite theorem. So let's start by talking a bit about the first approach, which is restricting the preferences, and then we'll spend a bit more time thinking about how computational complexity can play a role in circumventing this theorem. Okay, any questions so far? Cool. Okay, so here's here's just one simple setting, and I'll try to be very explicit about how it relates to the setting that we talked about because it is a bit different. So imagine that we want to choose a location for some public good, like a library, on a street. So the idea is, let's say, this is like a toy example, but like a bunch of people are living on some street, and we want to choose a location to build a library on that street. Each voter has an ideal location, which could be like where they live. Maybe they want the library to be very close to their house. Maybe they want it to be very close to their workplace because they still look up scientific papers in the library, which would be really a stretch. So you could have like many considerations to where's your ideal location, but each player or each voter has an ideal location for the library. And the way the utility function is defined, or the preferences are defined, is that the closer the library is to the voter's peak, to his ideal location, the happier the voter is. So, the way to think about this, or like how is this related to the setting that we talked about? So the set of alternatives is all possible locations for the library. So it's basically every real number. We're thinking of like the possible locations as the real line. So the set of alternatives is the set of real numbers. You can put the library anywhere on the real line. And what we're saying is, this type of preferences induces an order over the real line. So you can say, well, if the voter, so this is the real line, like all possible locations for the library, and we have some voter whose peak is at this point. So now if we're comparing this potential location to this potential location, then this rule tells us this location is preferred to this location. Okay, so this sort of induces, lets us to compare any pair of locations according to the preferences of the voter. But notice that it does have some structure. So for example, it can't be the case that, if this is my peak, then I'm saying, this location is preferred to this location, which is preferred to this location. Right? Things are sort of lie on the same line. So if you have multiple voters, this, and this one has a peak here, this induces some constraints over the possible orderings different voters can have for the alternatives. Okay? So this is a restriction. You can still think of it as voters have rankings over, it's uncountably many, so it's a bit tricky, but can compare like any pair of alternatives. However, the fact that we're assuming these peaks does impose some structure over the possible comparisons. Okay, so this is like on a high level why we're still basically in the same setting. It's just a bit messier because there's uncountably many alternatives, and we're imposing some structure on what the comparisons can look like. Cool. So let's think about the setting a bit. And I want to think about a few voting rules that are referred to as mechanisms in this setting. So these are rules that take as input the peaks of the voters. So basically every voter reports what's his favorite point, which defines his preferences. And they return as output the location for the library or for the public good. So here's an example. Let's say that the location, the peaks reported by the voters are these 5 points on the line. And the first mechanism, the first rule, is return the leftmost point reported by any voter. So in this example, this would be the leftmost point, the point returned by the rule. So here's another example. Let's take the midpoint between the leftmost and rightmost reported locations. So here, the leftmost reported location is this one, the rightmost is this one. So we're taking the average of these two numbers, the midpoint between them, which is over here. So this would be the location for the facility if people say these are our peaks. Okay, so these are both voting rules defined in the setting. Right? It is a bit confusing because their input is the peaks that actually define like the whole preferences of the voters. So it's the same as like taking as input the entire preferences. Any questions about like this model what these rules are doing.
So, is there a way of quantifying the happiness of a person here as well?
Yes. So so in some of the work on this, it's going to be less relevant for us. But you could say the happiness of a voter, like his cost, for example, his unhappiness, is some function of the distance between the good and his peak. So there's a lot of work in the L1 distance, just Euclidean distance on the line. But people have looked at many different distance functions on many different, much more general.
Isn't this like a strong assumption that the closer it is to the peak, the happier the person is?
Yeah, so it's a very strong assumption. We actually don't need it for the results that I'll tell you about. So essentially, like these results hold even if you just assumed what's called a single peaked assumption. That says, and this assumption also makes sense in a discrete, on a discrete set of alternatives. So it just says there is a way to order the alternatives, like one ordering for everybody, such that so maybe the ordering is like let's do just A, B, C, D, E, F, G, H, such that if I say, every voter has a peak, let's say my peak is E, such that if you look at two alternatives on the same side of the peak, then, then in this case, D, for example, would be preferred to C. So you can't necessarily compare D to F, like it doesn't impose a restriction on D versus F. But if you look on the same side of the peak, then you have the restriction. And this kind of restriction is actually enough for the positive results that we'll talk about. Okay, but just to simplify the exposition, I'm making this very strong assumption. It's a great question. Any other questions about this model? Okay, cool. So here's a question to you guys. We talked about two rules, left point and midpoint. Which of these two rules is strategy proof in this setting? Now that we're almost done with my lectures, I can reveal to you my secret, which is when I say 10 more seconds, so basically I wait for 60 votes, and then I say 10 more seconds. So if you just don't vote, you can make the lecture go on forever. You can try it out next time. Okay, so let's see what we got. Good, excellent. So we have a majority for the right answer, which is only leftmost. So let's see, so why for midpoint, why is midpoint not strategy proof? So how could we gain from manipulating? Like what's the intuition? Yeah.
If you needed some point that's close to the midpoint like of the other votes, but let's say slightly to the right, you could vote like on the extreme right side and that would skew the midpoint.
Excellent. And what's your name?
Devdeep.
Devdeep?
Yeah.
Right, so Devdeep is saying, basically by going, if you wanted, so I guess the situation you're describing is like you want the midpoint to be, like you have this peak, but then other people are maybe here. Is that what you have in mind?
Yeah.
Right. So like, a bunch of players are here and you want it to be here. The midpoint would be between the leftmost point and the rightmost point, which is this one. But then Devdeep is saying, but you can skew the outcome towards you by, for example, if you double the distance, like you went further to the right, then this would move the midpoint. You can even move it like to be exactly on your location. Right? So you can sort of drag the midpoint with you by moving to the right and drag it closer to you, even get it to be exactly on your location. So this would not be strategy proof. You can get the outcome to be closer to you to make yourself happier by lying about your location. Yeah.
What if you did not know what the others were voting?
So that's a big question. Then the big question is, how do you reason about what you do know about how others are voting? So you could, for example, say you have some probabilistic information about what others are doing and so on. That's, there's plenty of work in this direction, but we won't go in that direction. I mean, let me just say that, of course, you can get some more positive results by going in that kind of direction, for example, making probabilistic assumptions, but not a lot more. So the Gilbert-Satterthwaite is actually very robust, for example, to saying I only have probabilistic knowledge about what others are doing. It's actually very impressive, like how robust this theorem is. Good. So let's talk about leftmost point. So I claim this is actually strategy proof, and a lot of you are claiming that as well. So what's the intuition for why taking the leftmost point is strategy proof? Yeah.
So if you are the leftmost point, there is no point lying about it because you already got your choice. If
Excellent.
you're not the leftmost point, you can lie and make your location leftmost point, but that just pushes the lie further away.
Yeah. Perfect analysis, right? So there are basically two options. If if we're looking, we have a situation like this. If we're already, like we're taking the point of view of the guy who is the leftmost point, they're getting what they want. They obviously can't gain by lying. But then the idea was, if it's anybody else, the only way in which they can affect the location of the leftmost point is saying, oh, I'm actually to the left of that point. But then if the facility was here before, it's only pushing the facility further away, and that's only making things worse for themselves. So the only way in which you can make things, you can affect the outcome is by making things worse for you, and therefore you do get strategy proofness. Okay, so this is already like one mechanism that is, non-dictatorial. Yep.
So it seems to me kind of like the difference between the leftmost and the midpoint strategy is similar to the difference between like dictatorial and plurality strategies, in that like it kind of chooses one voter to take their preference and just ignore everyone else's.
Yeah, so I agree in the sense that there's no aggregation. I disagree in the sense that this is not fixing any particular voter, right? So this is saying, so I think this intuition is misleading overall, because we'll see another example that is strategy proof because of similar reasoning where there is more aggregation in a sense. I would say like here, the fact that it's choosing the location of one of the voters, this restriction is called peaks only. It's just saying, okay, I mean, it's sort of very natural to say we have a bunch of voters, we'll choose the location of one of them. But unlike dictatorship, it's not blindly looking at the same voter, it's sort of looking at the entire picture and deciding based on that. So I think this comparison is a bit misleading. Let's look at another example and we'll see if you still have the same intuition. Okay, so this is an even better mechanism, but sort of the same intuition works here. So we said, leftmost point, that was nice, like that was strategy proof. But let's instead look at the median peak. Okay, so in the case of 5 voters, we're looking at the median among them, which is the third from the left or the third from the right. Let's say an odd number of voters to make it simple. If you have 7 voters, it would be the fourth from the left. So let's think about this one, right? So first of all, I want to claim the median peak. If you look at all of the possible alternatives, all of the points on the line, this is actually a Condorcet winner in the sense that it's preferred by a majority of voters to any other point on the line. Why? So, think about the median versus some point to the left, let's say this one. So these 3 voters prefer the median to this point, right? It's closer to them than this point. And if you look at some other point to the right, like this one or this one, then these 3 voters prefer the median to that point on the right. So any direction you go, left or right, you have a majority of voters who prefer the median to the point, to this other point. So this is actually a Condorcet winner over this uncountably large set of alternatives. Another thing, like the leftmost point, this is an onto mechanism. So, the median can be any point on the line. For example, everybody could be in the same point, the median will be there. So we're not saying, there's no point that can't be selected when we choose the median of the reported locations. So this is onto. And finally, I want to convince you, of course it's non-dictatorial, okay? So, and not only non-dictatorial, it's looking at like the complete picture, right? And saying, this guy is the median. So I feel like it is like intuitively different than dictatorship in that sense.
it's still choosing one specific person.
Yeah, right. So that's more like the speaks only restriction. To me, intuitive, it seems different. Yeah, I mean, my intuition is that's not where strategy proofness is coming from. But yeah, I mean, I think it's a valid point. I mean, I guess one way to say this more rigorously is there are rules in the setting that are strategy proof and do not choose any of the peaks. So for example, one thing you can do is you can have phantom voters, which are numbers that are predetermined, and then you take the median of the reported locations and the phantom voters. And this would also be strategy proof. Right? And that doesn't choose necessarily any of the actual voters. So I think maybe that's one rigorous way to say, like, that's not where the strategy proofness is coming from. I think it's coming from this k-order statistic thing. Okay, so basically any k-order statistic is, like the median or the leftmost among phantom voters and real voters is strategy proof because of the same reasoning, which we'll come back to on the next slide.
It's kind of still saying that we're picking one particular point and ignoring everybody else. Kind of.
I mean, but that's just how a rule is defined in the static. So
this is like that intuition that we're talking about that is very similar to dictatorship. It's kind of the majority is that we're actually taking into account everybody, and here we're basically ignoring everybody except one guy.
But you aren't ignoring like a predetermined set of people, right? It's dependent on
It's
exactly.
not predetermined.
Right. I mean, plus the identity of the median would depend on what everybody else thinks. Right. So let's do the next slide as well, and then I think that there's really some k-order statistic intuition that we'll see on the next slide too, which is really what's playing a role here. Okay. So first of all, notice that the median is onto a non-dictatorial, like the leftmost point as well. So if we can show it's strategy proof, I just want to say explicitly, we're saying the Gilbert-Satterthwaite theorem doesn't hold in this setting. Here are rules that are onto non-dictatorial and strategy proof. Specifically, the median is also has this Condorcet property, which is really nice. Okay, so why is it strategy proof? The picture is very similar to what we had for leftmost reported location, slightly different analysis. So, if you're the median, you're obviously happy, right? If you're somebody else, let's say you're this guy, and you want to try to manipulate the outcome, well, if you report any point that's, you started to the left, you report any point to the left of the median will still remain the same, so you don't affect the location of the median. If you report, so your only way of affecting the outcome is reporting, saying, oh, I'm not actually here, I'm actually to the right of the median, then you can become the median, or, if you said that you're even to the right of this point, the median would become this point. But the only thing you're doing here is pushing the median away from your actual location. So it's the same kind of reasoning that helped us with the leftmost point, and I think that's really what's playing a role for strategy proofness here. Okay, so that's all I wanted to say. I mean, there's a lot more to say about this, but just to give you a taste of why restricting preferences allows us to circumvent Gilbert-Satterthwaite. So I want to spend the rest of the lecture talking about complexity of manipulation and how we can use that to circumvent Gilbert-Satterthwaite. Okay, so what the theorem tells us is that manipulation is always possible in theory, right? But the big question, the big idea was, can we design voting rules where it's difficult in practice? So another way to phrase this is, are there reasonable voting rules? Of course we can come up with crazy voting rules that would be hard to manipulate, but are there reasonable voting rules that we actually want to use, or people have talked about as good voting rules in social choice, that are hard to manipulate from a computational complexity viewpoint? And the idea behind this is, if manipulation is a very hard computational problem, voters would just default to telling the truth. Okay, like if you can't figure out how to lie in a way that gives you a better outcome, it's quite likely you'll just say, well, I might as well just report my actual preferences. So that's the kind of reasoning behind this. And this sort of says, if we can design voting rules that are actually hard to manipulate in practice, this could go a long way in circumventing the Gilbert-Satterthwaite theorem. So saying, okay, it's a problem in theory, but we're using computational thinking to say, well, for these voting rules, this is actually not going to be a big issue in practice. Okay, so that's sort of the high-level approach here. It was proposed by Bertoldi, Tovey, and Trick. Mike Trick is actually a professor here at CMU at the Tepper Business School. He specializes in integer programming, but he, around this time, they came up with this cool idea and had a couple of like groundbreaking papers trying to apply this idea to social choice. Okay, so in order to talk about computational complexity, we need to define the manipulation problem formally. So the manipulation problem, let's call it F manipulation, which is the problem of manipulating the voting rule F. So it's specific to a voting rule. And it's defined as follows. We take the point of view of a manipulator who's trying to get a better, or trying to get some outcome for the election. The manipulator, like in the game theoretic setup, it's a worst case setting, so he knows exactly how the other voters are voting, the non-manipulators, or the other voters. And the manipulator also has a preferred candidate P. And the question is, can the manipulator cast his vote in a way that makes P win the election? So for example, let's take Borda as our voting rule. So we were thinking of the Borda manipulation problem. And let's let the preferred alternative be A, and our manipulator is voter number 3. So an instance of the problem can be something like this, where we're told the manipulator is voter number 3. Here are the votes for the other voters. The preferred alternative is A, and the voting rule is Borda. Can voter 3 cast his vote in a way that makes P win the election? So that's exactly the example that we saw before, and we saw that the answer is yes. If voter 3 casts this vote, then A wins the election. So this is a yes instance of the Borda manipulation problem with these parameters. So saying the manipulator is voter 3, and A is the preferred alternative. Okay? So just one small subtlety that's not really crucial is that the word uniquely here. So when we think about voting rules like Borda that have a notion of score, just to avoid some annoying issues, I'm being explicit and saying we want P to be the unique winner of the election in terms of having the highest score under Borda, for example. Okay, so we don't want it to be tied with some other alternatives for Borda score. And it would be the same for Copeland or plurality or Maximin or a lot of these score-based rules that we talked about. Okay. Everybody okay with the definition of the manipulation problem? Cool. So what I want to do is introduce an algorithm that attempts to solve this problem. Okay, so we're given an instance of this problem, and we're being asked, under this voting rule, given these votes, given this preferred alternative, can voter number I cast a vote that makes P win? So this greedy algorithm tries to construct a vote for the manipulator that would make P win under the given voting rule. And it sort of does it iteratively by placing alternatives one after the other in slots. And if at some point it sees that it can't make P win, then it just says, oh, there's no manipulation. Okay? So here's what it does specifically. It first puts P first. Right? So it puts the preferred alternative in the first place. Now, as long as it has some unranked alternatives, it asks, of the unranked alternatives, if there's an alternative that can be placed in the next spot without preventing P from winning, when you look at the scores of the different alternatives, then it puts that alternative greedily in the next place without looking at anything else. If it can't put any alternative in the next place, it says no, there's no manipulation. And if it was able to complete the whole ranking, then it says, yes, it is possible to make P win. Here's the ranking that does it. So notice that if this algorithm says, yes, there is a manipulation, it's always right, because it's constructive. It was able to make P win by constructing a ranking. If it says no, it might make a mistake because it's greedy. Right? It could be the case that it just tried this order, but maybe a different order would have worked, and it got stuck because of being greedy. Yeah.
Are we thinking about applying this algorithm to the general setting, or to the Borda, or to the ranking score?
So we want to apply it to the F manipulation problem. And the question we're going to ask is, for which F does this work? Okay? But this algorithm is defined for this problem in general. I guess as long as the voting will satisfy some conditions, it's well defined. But the question is when would it work? Okay? So let's do a few examples of this algorithm for 2 voting rules, and then we'll see when it works. So Borda, let's apply this algorithm to Borda and the example that we had before. So, it tries to get A to win. It's building the ranking of voter 3, and it starts by putting A first. Now it's asking, can I put B in the second position? It's like, well, if I put B in the second position, B would have 8 points. A has only 7, so that would prevent A from winning, so that's not good. Can I put C in the third position? Yeah, because C has only like 2 points plus 2 points from here, that would be 4 points, so A would still have the highest number of points. So I can put, so I'm trying to put B, I can't. I try to put C, that works. Now I'm asking, okay, for the next position, can I put B here? And the answer is again no, because if I put B here, B would have 3 plus 3 plus 1 points, that's 7. A also has 7 points, so that would prevent A from uniquely winning the election, right? We didn't want a tie. So B doesn't work, so then it's asking, can I put D in the next position? So of course, yes, like D would have only 1 point, that's fine. And finally, it's asking, can I put the last alternative B in the last position? And then it's fine, because B has only 6 points, A has 7. So at this point, it says, great, I found the manipulation. I was able to make P win. Okay, so that's how this algorithm applies to the example that we saw for Borda. Let's look at a more complicated example for Copeland. So let me remind you how Copeland worked. We said a pairwise election between two alternatives, X and Y. So X beats Y in a pairwise election if a majority of voters prefer X to Y. And we said Copeland is the rule that selects the alternative that beats the largest number of other alternatives in a pairwise election. Okay, so your Copeland score is the number of alternatives you beat in a pairwise comparison, and you want to select the alternative that maximizes the Copeland score. So let's see how this algorithm would work for this rule. So what we're given here, what we're given is, so we're saying the manipulator is voter 5. These are the votes for the 4 other voters, which we know. The preferred alternative, like before, is alternative A. And what this table is showing is the pairwise comparisons between different alternatives in terms of how many voters prefer the alternative in the row to the alternative in the column. So for example, for A, let's see, once we put him here, so we know 5 will rank him above everybody else. We don't know yet how the others will be in voter 5's ranking, but obviously A will be ranked above them. So if we compare A to B, you can see that voters 1 and 5 rank A above B, and the others rank B above A, so we have a 2 here. A versus C, so we have voters 1, 2, and 5 ranking A above C, so we have a 3. A versus D, so everybody, including 5, ranks A above D. And A versus E, so we have voters 1, 2, and 5 ranking A above E, so we have a 3 here. Now, B is going to be a bit trickier because I haven't put him yet in 5, and it's going to depend on where I put him in the vote of 5. So far, for the others, I just counted without voter 5. So for example, if you look at B, so B versus A, we also already counted 5 in favor of A. But B versus C, so we have voters 1 and 2 ranking B above C, voters 3 and 4 ranking C above B, and voter 5 I haven't counted yet. So we have a 2 in B versus C, and similarly for D and E. Okay, so all of the comparisons that are not against A, I'm not counting voter 5 yet. Cool. So now let's look at the next position, and let's say that I try to put alternative B here. So what would happen if I put B? Let's see. The row, what would happen to the row of B? So B would get another vote against C, D, and E. Right? If B is second, is definitely ranked above these other alternatives in this vote. So B would get another vote against C, D, or E. So this would become 3, this would become 5, and this would become 3. And that would mean that actually B would be a Condorcet winner. B would beat everybody, and in particular would be a Copeland winner. Notice that the Copeland score of A is 3, so he loses to B, but he beats C, D, and E. So what we need is everybody else to have a Copeland score of less than 3. But obviously, like, putting B in the next position would be bad. So let's try putting C in the next position. So what would happen if we put C here? C would get another vote against B, D, and E. So this would become 2, 3, 4, 2. right? And then the Copeland score, this would be 3, this would be 4, the Copeland score would be 2. C would still beat only 2 alternatives. So putting C in the next position is fine, right? And then I've incremented like the relevant entries. But C has a Copeland score of only 2, A has 3, so that's fine. So what about the next position? If I put B here, then B would get an additional point against D and E. So this would be 5, this would be 3. But then the Copeland score of B would be 3. He would beat A, D, and E. And that's not good enough because that would be a tie with A. So I can't put B in the next position. But I could put D. So this increases D's score against B and D. So this goes from 0 and 2 to 1 and 3. But still the Copeland score is only 1, and that's fine. So this is okay. And again, you can check, I can't put B in the next position. That would prevent A from winning. We can put E in the next position. And finally, when we put B in the last position, so we're not actually incrementing any of these numbers. So we can do that. And then the Copeland score of B is only 2 because it only beats A and D. So that's fine. A has a Copeland score of 3. Everybody else has less than 3. And A is the winner of this election. Okay, so this is a slightly tedious example, but just to show you, how this algorithm works on a voting rule that is very different from Bourda. And it still sort of made the right call on this example. But then, of course, Alex's question was, okay, these are a few examples. We saw for Bourda it works on one example, for Copeland it works on another. But what are we trying to say something general here, or is this just specific examples? So my claim is that this algorithm would always decide the manipulation problem correctly for Bourda, would always decide it correctly for Copeland, and would decide it correctly for a bunch of other rules that satisfy this slightly hard to digest condition. So let's talk about it quickly, carefully and slowly. Let's see. Okay, so the scenario here is we fix the voter I, who we think of as the manipulator, and we fix the votes of all of the other voters. Okay, so all of this stuff is going to be fixed, and we're going to reason about how the voting rule, like which alternative it chooses, based on the vote of voter I, but everything else remains fixed. Now, we assume that the voting rule has the following property, that there's some function S, which we think of as a score function, that takes as input the vote of voter I, remember we fixed everybody else's votes, and the name of an alternative, and it has the following properties. So first, the voting rule F chooses the alternative that has the highest score. Okay, so what this is saying, it's sort of a score-based rule, and all it does is, all property 1 is saying is it chooses the alternative with the highest score. Okay, so it chooses a candidate that uniquely maximizes the score. And again, there's a subtlety here with uniquely. Okay, so I want to define the score function in a way that the scores would always be unique, that there won't be any tie breaking. We'll come back to this point in a minute. The second property is a bit more confusing. So essentially what this is saying is that the score of an alternative depends on the alternatives ranked below it. And specifically, it's kind of a monotonicity property in the score. So what it says is if you look at two rankings for the manipulator, smaller than and smaller than prime, and these have the property that everybody who is ranked below X under this ranking is also ranked below X under this ranking, then the score under this ranking is at least as high as the score under this ranking. Okay, so it's basically saying, if there are at least the same and maybe more alternatives ranked below you, your score can only be higher. And intuitively, this says, your score basically depends on the set of alternatives ranked below you. Okay? Okay, so this is confusing, definitely. So let's think about this a bit. Just maybe to state the conclusion of the theorem says if F has these properties, then it correctly decides the F manipulation problem. So for any voting rule that satisfies the score kind of property, the algorithm would always be right, in the sense that even though it's greedy, if it fails, then there is no manipulation. Like there's no smart way to rank the alternatives that would make P win. But let's just spend a minute thinking about these weird conditions. So for example, let's think about Bourda count. right? And I want to claim that Bourda satisfies these conditions. But to be more concrete, I have to define how tie breaking would work. So let's take a simple tie breaking method. Let's say that, let's call the alternatives A1, A2, up to AM. And I want to break ties in this order. So if there's a tie between two alternatives, I'm going to choose the one with the smaller index. Okay, this order is my tie breaking order. So the question is, what would be a score function for Bourda that would satisfy these conditions? Or for Bourda with this particular tie breaking method? Because a hint is that Bourda already has like a pretty clear notion of score, right? So the main difficulty is this tie-breaking thing.
You could just multiply your normal Bourda scores by m or by some large number, and then add plus the index of m
Excellent.
minus. I mean,
Excellent. Yeah, that would work great. So what Alex is proposing is let's take the Bourda score, Bourda of x times m. Let's say m plus 1. Yeah, m would actually be fine. M plus 1 to be safe. Yeah. And then add, so of ai. And then add I.
probably m minus I, because you want first one to
Oh, right.
test.
Good.
So, yeah.
Good. Excellent. Okay, excellent. Yeah, I had in mind something like Bourda of ai plus 1 over I. Right, but both of these are fine. So it's just saying like we basically rank them according to Bourda's score, but then we have, we build into our score function this additional bonus that depends on your index. But notice that this bonus is not enough to push you over an alternative that had higher Bourda score. Right, so that's why we multiplied by m minus 1, m plus 1 in Alex's scheme. So it's saying, the maximum bonus you can get is m, and I guess m minus 1 anyway, m would be fine here. Let's multiply by m. Okay, the maximum bonus you can get is m minus 1 in the scheme, and therefore it's not, like if you had lower Bourda score, it's not going to be enough to make the difference, but if you have the same Bourda score, then it's enough to break ties. Okay? But I think like the main takeaway, there's just this annoying complication with the uniquely and tie breaking and stuff, but really the intuition here is voting rules like Bourda and Copeland have a very natural notion of score, and all this is saying is, the score function is just, the natural notion of score up to, maybe you need to build tie breaking into the score. Okay, so it's like sort of very natural that the score function of rules like Bourda and Copeland satisfy these conditions. Okay, and that's exactly what allows us to even define the algorithm well, right? So when we say, right, that's sort of going back to your question before. So when we say like, is it okay to put the alternative in the next place, we have to know that it doesn't actually matter what happens below, and that's basically because of property 2. Good. So any questions about this statement? We're going to prove the theorem, but any questions about the statement of the theorem? Yeah, I do want to prove it because it's a very simple proof, and I think a very powerful result. It's one of these really cool things where it's just like a 2-slide proof, but like a very, very strong statement, a very general statement. So let's see the proof. Like I said, a very simple proof. So remember that we don't have to worry about the case where the algorithm succeeds. When it builds a ranking and says there is a manipulation, yes, this is a yes instance. It's always right because it's a constructive algorithm. So we just need to worry about the case where it said there is no manipulation, but it was wrong because it's a greedy, stupid algorithm. So let's say that the algorithm failed and at some point got stuck. So it started ranking the alternatives. It put P first and then B and then D and then got stuck. Right? So the other alternatives here are A and C, but it couldn't put either A or C in the next position. And let's say for contradiction that the algorithm was wrong, so there is actually some ranking smaller than I prime for the manipulator that does make P win the election. And this is what this ranking looks like. So P happens to be in the second place, which would be kind of silly, but whatever. And this is the ranking, and P wins the election under this ranking. Now, let's define by U the set of alternatives that we couldn't actually rank in this ranking. So we got stuck at some point. In the example, we couldn't rank A and C. So let's call these alternatives U. And this is pointing to A and C, which are the alternatives that are not ranked in the original ranking. So U source stands for unranked. And let's call small u is going to be the highest ranked alternative in U according to this ranking that actually makes P win. So in our example, the set U is the alternatives A and C, which are not ranked here. And of the two, A is ranked above C in this ranking. So our small u is going to be A in this example. And essentially what we want to show is that it should have been possible to put u in the next position here without getting stuck. Like this, putting u in the next position shouldn't prevent P from winning the election. So what do? We complete this ranking by putting u next and then adding the other unranked alternatives in u in some arbitrary order. Okay, and again, we want to get a contradiction by saying, this should actually been fine, at least putting u in the next position. Like you shouldn't have been stuck at that point. So this follows from three very simple inequalities, just putting them together. So the first one is saying, right, so let's look at this ranking versus this ranking. Here, P is ranked first. Here, P maybe is ranked first, maybe not. But definitely the set of alternatives ranked below P in this is a superset, in the weak sense, of the set of alternatives ranked below P in this ranking. Right? Because P is ranked first, it's ranked above everybody. So the first property tells us that the score of P in this ranking is at least as high as the score of P in this ranking. And just going back to the second property, it said, if we have the situation where the set of alternatives ranked below you is a superset in this ranking compared to this ranking, the score can only be higher. Okay, so we just apply it here, and we have this inequality. Now, the second inequality says, well, we assumed that this ranking makes P win. And remember that we always choose an alternative that uniquely maximizes score. So this says that the score of P in this ranking is strictly higher than the score of U. Right? Just because P1, we assumed that this was a ranking that makes P win. And finally, the third property is, again, we appeal to property 2, the third inequality. So we're saying, again, comparing these two rankings. In this ranking, U, small u, is ranked above capital U, as well as possibly some other alternatives. Right? Like in this example, capital U is A and C, and small u, which is A, is ranked above C and also above D. In this ranking, small u is ranked exactly above the alternatives in capital U. Because we said that capital U is the alternatives that are not ranked here. We put small u first and then the rest in some arbitrary order. But again, we have the property that the set of alternatives ranked below small u in this ranking is a superset of the set of alternatives ranked below small u in this ranking, which is exactly capital U. And therefore, by the second property, we have that the score of u in this ranking is at least as high as the score in this ranking. So now we just put these three inequalities together. So we have this is greater than this, this is greater than this is greater than this. So putting them together, we have that the score of P in the original ranking is at least the score of u in the original ranking. Which means we could have put u in that place in the original ranking without preventing P from winning, which is a contradiction to how the algorithm works. Okay, so very elegant proof, I think. Very simple, and yet pretty powerful in capturing quite a few rules. So for example, this would capture any positional scoring rule. I think I mentioned this term maybe, which includes plurality, Borda count, and a bunch of others. It would capture Copeland, it would capture Maximin, it captures like a whole range of voting rules. So it's a very powerful statement. And this basically says, the negative interpretation of this theorem, remember what our goal was. So we wanted to find voting rules that are hard to manipulate. And what this voting rule says is for this wide range of voting rules that satisfy that property, they're actually easy to manipulate. Not only easy, we can just run this silly greedy algorithm, and that will correctly determine the manipulation problem. So this is a negative, it sounds like a positive result because we have a polynomial time algorithm, but it's actually a negative result in saying all of these rules will not be able to help us achieve our goal of finding a rule that is hard to manipulate. But the good news, and with this we'll end, is that there are, like over the years, people have actually found voting rules that are hard to manipulate. So here are a few examples. One somewhat strange example is Copeland, but with second order tie breaking, which means that you break ties according to the Copeland, so what you do is you look at like the Copeland score of alternatives you beat, and you add those up to compute your score. So basically you first look at the Copeland score. If two alternatives are tied, you look at the Copeland scores of alternatives you beat, add them up, take that as your score, and that makes the manipulation problem NPR because of annoying tie-breaking issues, so it's not that exciting. A much more interesting rule and result is STV. So STV is hard to manipulate. So remember, that's the one that proceeds in rounds. And then in the first round, we look at the probability scores, eliminate the alternative with the lowest score, and then continue doing that until there's only one alternative remaining. And we said, in the US, this is called ranked choice voting. It's used in Maine. It's used in cities like Cambridge and San Francisco. This is like a serious voting rule used in practice. We talked about the referendum in the UK where they rejected this rule, but it's a voting rule that many people use and talk about. And this is a really cool result because it says, like, even from this computational complexity viewpoint, this is like a very nice property in addition to other properties for this rule to have, that it's hard to manipulate, even though, of course, computing the outcome of the election is pretty easy. And one reason why this rule, why this doesn't fall prey to the theorem is that this rule is not monotonic. Not only in the sense of the score, it's even in the sense of like, you can push an alternative upwards, but make it worse in terms of the outcome of the rule. So, it's just like a slightly weird rule in that sense, which doesn't satisfy the conditions of the theorem. And in particular, turns out it's hard to manipulate. Another rule that I didn't tell you about, and I'll just use the last few minutes to tell you about, is a voting rule called ranked pairs. So the algorithm for this one is as follows. We look at all of the alternatives, and we look at the pairwise majority graph, which tells you the margin in terms of how many voters prefer X to Y, minus how many voters prefer Y to X. So the difference between the preference for the two alternatives. We look at that graph. And then we sort the comparisons in that order, so we can think of it as edges in the graph. I'll show you on the next slide. And then we basically go by strength and lock in edges, unless locking in an edge creates a cycle. If it does create a cycle, we lock it in the opposite direction. And we keep doing that until we get a tournament, basically, which is a complete acyclic graph. And then we take the order induced by that tournament, and we take the first alternative in that order. So let me show you an example. Let's say that the numbers on the edges are the results from the pairwise comparisons between the alternatives. So this, for example, says if you look at the number of alternatives that prefer A to B versus the number of alternatives that prefer B to A, the first number is larger by 6 than the second number. Okay, so the difference is 6. The edge pointing this way says like A is preferred to B by the majority. So, look at these numbers. The highest number is 12. So we start by locking in this edge. So B is preferred to D. Now, the second highest number is this 10. So we lock in this edge. The third highest is 8. So we lock in this edge. The fourth highest is 6. I think here, like locking this in still doesn't create a cycle. We can lock this in as well. But now, the next edge is this one, but if we locked it in the right direction, we would get this cycle, ABC. So we have to lock it in the opposite direction, which is what we do. Then this edge, if we lock it in this direction, we would get this cycle. So we can't, we have to lock it in the opposite direction. So at this point, we have a complete acyclic graph. And now how do we interpret it? So notice that C beats everybody in this graph. Let's see, A beats B and D but loses to C, so he's like second place. B beats D but loses to the other two, so he's third place, and D loses to everybody. So any complete acyclic graph you can interpret in this way as an order, and then we take the highest ranked alternative in the order, which is alternative C. He would be the winner of the election. So this bizarre rule was defined to satisfy some social choice properties of the type we talked about last time. It actually satisfies some properties that are pretty hard to satisfy, but it's like a nice rule that is used by some organizations, and this is really cool to know, I think, that it also has this property of being hard to manipulate. Great, that's it for today. See you next time.